Hey, what's up guys? Mr. Miasis here, and we're going to talk about Taylor and Maclaurin series in this video. So I'm going to explain to you what a Taylor and a Maclaurin series are and the Taylor polynomial expansion, but let's not try to get too confused. Basically, here's what's going on. We're going to have a polynomial function, and we're going to take this polynomial and we're going to try to approximate that regular function, f of x, with a polynomial. All right, so it's almost like we're taking a transcendental function like e to the x or sine x or pi to the x or something like that, and we're going to turn it into a polynomial approximation. Like a polynomial isn't going to be perfect, but it's going to approximately be close. And in order for that to happen, we're looking at some x value. Now we'd want those y values to be pretty close, right? That's kind of what we're trying to approximate. But to get a really good approximation, we've learned that we could take a derivative, and if the slopes are the same, then we're going to get a pretty close approximation. In fact, for better accuracy, we could take the second derivative, and if the second derivative, the concavity is the same of the polynomial and the transcendental function, then we're going to get an even better approximation. If I take the third derivative, we're going to get an even better approximation, and so forth. So if I keep taking derivatives, then I'm going to be able to come up with a polynomial function that's going to be a pretty close approximation. Now, this kind of goes back a little bit. We've done a little bit of this, and you don't really know you did it because I kind of hit it. If you're in my class, in a few videos ago, we did an example of where I showed you a series that if we took the derivative of that series, we ended up with the same series again. And we said, okay, well, since we have the derivative of a series that's the same as the series, then that function must be e to the x. So it kind of showed you what the function e to the x looked like as an infinite polynomial. Excuse me. We also did one of inverse tangent in the problems that we were doing using integration. But basically, we were looking at the series and how the series looked to be the function. This Taylor series and Maclaurin series actually show us how we get those series to represent that function. Okay, so we have a Taylor series, which is what we call centered around a certain value of c here. Okay, and then a Maclaurin series. In Maclaurin series, the c is equal to 0. That's the only difference. And a Maclaurin series is actually easier because we're only looking at f of zeros, f prime of 0, f double prime of 0. Where in a Taylor series, this c might be something else like 2 or 4, just not 0. But these are going to be values, okay? This is the part that we're going to have that polynomial in. So let's take a look at a couple examples of using the Maclaurin series. All right, so for example 1, I'm going to use the definition of the Maclaurin polynomial that I just had, and we're going to find a fifth degree Maclaurin polynomial. And we're going to do this for the function e to the x. So what I'm going to do is I'm going to make this little table here, and I'm going to find e to the, we're going to first label f of e to the x, and I'm going to find f of 0, so e to the 0 is 1. And then I'm going to take the derivative. And then I'm going to take the derivative again, and I'm going to take the derivative again, and then the next derivative, and the next derivative. I got to do it 5 times. I'm looking for the fifth degree Maclaurin polynomial. These are all going to be 1, just like before, right? E to the 0. Okay, so according to the Taylor, the Maclaurin polynomial, it's f of 0 plus f prime of 0. So f of 0 is 1. Plus f prime of 0, which is 1 times x, plus f double prime of 0, which is 1, over 2 factorial times x squared. Okay, I'm going to write the rest of it down here where I need my polynomial. So I have 1 plus x squared over 2 factorial plus x cubed over 3 factorial. Plus x to the 4th over 4 factorial plus x to the 5th over 5 factorial. Okay, and I'm going all the way up to here. And my 1s are right here too. 1, 1, 1, and this is my fifth degree Maclaurin polynomial. Fifth degree because I have x to the fifth, right? Now, this polynomial actually, this is a good approximation for e to the x. But it's not exact, right? It's not exact because, it only goes to the fifth degree. But if we continue to do this over and over and over and over and over again, we're actually going to end up with the, we're going to end up with an infinite series. And this infinite series ends up being the exact correct approximation instead of just a good approximation. So we have a good approximation, which is the Maclaurin series to a certain degree polynomial. And then we have the exactly correct approximation, which will be our entire series. 1 plus x squared over 2 factorial, 3 factorial, plus dot, 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 x to the n over n factorial, plus dot, 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 right? So by going out to infinity, we've created an exactly correct approximation of the function f of x equals e to the x using a Maclaurin series. Let's take a look at one more example in this video. Oops. Okay, actually, that was the only one I was going to go over. In my next video, I'll go over a Taylor series example, and then we'll see the difference between the two. All right, catch you guys later. Bye.